Good evening once again. We will get started. This is SK Ghosh. I would like to welcome each and every one of you to the continuation of this training and capacity building activity of Project S, of a component S9 of Rajuk's Urban Resilience Project. This is the continuation of structural instruction. Today is module S5. Yesterday, we started on seismic design by BNBC 2020. Uh, I was unable to take you through all the material that I had prepared for yesterday. Time ran out. So we will start today with where we left off yesterday, and then I will go on to a discussion of the irregularity provisions of BNBC 2020, how you go about designing irregular structures. And that will probably be it for the day. I have a significant segment on non-building structures and non-structural components. That is in the slide set, but I have no expectation of being able to cover it because of time limitations. So that material is for your use, but we won't have a chance to discuss it together. So we were towards the end of our discussion of the equivalent lateral force procedure of BNBC 2020. The equivalent lateral force procedure is in section 2.5.7, which is in part 6, chapter 2 of the code. We will start with what is commonly referred to as drift check, which is an integral part of seismic design by ASC 705 or BNBC 2020. The interstory drift have to be kept within tolerable limits. Most of the seismic design provisions of the code are life safety provisions or collapse prevention these days. Remember, we design to prevent collapse in the maximum considered earthquake. Most of the provisions are directed towards ensuring that. But two places in the code, we go beyond strict life safety. Once, when we introduce an importance factor larger than one in the design of higher occupancy category structures, and second time when we do a drift check, the purpose of which is to make sure that non-structural components are not damaged because of too much interstory drift. This then, if the non-structural components and the equipment supported on the roofs are not damaged, then there is reasonable expectation that the facility will go on functioning during and following an earthquake. There is a control of property damage aspect also to drift check. So this is beyond life safety. I do want to emphasize that. Now, interstory drift is the deflection at the top of a story minus the deflection at the bottom of the same story. That is the first thing. Exactly what deflection we will talk about in on with this slide. So we in seismic design start out by calculating or in the equivalent lateral force procedure start out by computing the design base shear V. We distribute that along the height of the structure in the manner prescribed by the code. When we distribute V along the height of the structure, we get F sub x forces, capital F sub x at floor level x. We elastically analyze our structure under those distributed forces. That analysis gives us two very important things. It gives us bending moments, shear forces, axial forces at various critical sections of various structural members. The generic notation for which is capital Q sub capital E. Q sub E is bending moment at a beam section. It is shear force at a column section. It is axial force in a column. It is generic notation for all internal forces. The same analysis will give us lowercase delta sub xe, which is the elastically computed deflection at floor level x. So delta sub xe, very important notation, E for elastically computed. Delta sub xe is elastically computed deflection at floor level x under the code prescribed seismic forces, which means the design base shear of the code distributed along the height of the structure in the manner prescribed by the code. Okay. This delta sub xe, as I mentioned yesterday, is not the deflection floor level x will actually undergo if the design earthquake were to hit our structure. Our estimate of the design earthquake displacement is the elastically computed delta sub xe multiplied by the deflection amplification factor C sub D, which is given in the R values table. Okay, so C sub D times delta sub xe is our estimate of design earthquake displacement. Now we divide that by the importance factor I to take the occupancy of the structure kind of out of the picture. The ultimate idea is interstory drift has to be kept within tolerable limits, which is the upper equation on the page. The tolerable limits in AC 705 and in BNBC 2020 are a function of the occupancy of the structure. We have much tighter limits on interstory drift in a hospital than in an office building. In a hospital, the interstory drift has to be kept within 1% of story height, whereas in an office building, we are allowed to go up to 2% of story height. Since the limits themselves are a function of the importance of the structure, we should not penalize the structure twice. Once by instituting a tighter drift limit for a more important building, and second time by calculating a larger drift for an important building, because the forces under which you are calculating the drift are enhanced, are increased by an importance factor I. So we divide the computed deflection by the importance factor. The C sub D delta sub xc divided by I is denoted by delta x. That delta sub x at the top of a story minus the same delta sub x at the bottom of the same story is the interstory drift delta sub x for story x, which is the story directly underneath floor level x, has to be within tolerable limit delta sub a. Okay, so this is everything I said is terribly important. So we start with elastically computed delta sub xc. We amplify that by deflection amplification factor C sub D. We divide that by I. This C sub D delta sub xc times I is delta sub x. delta sub x at the top of a story minus delta sub x at the bottom of the same story is the capital delta sub x interstory drift for story x that has to be within tolerable limit. The notation is explained on this page. I have given you ASC 7 section number, table number, etc. And the same thing for BNBC section numbers. The table of allowable deflections is table 12.12-1 in ASC 705, table 6.2.21 in BNBC 2020. Identical table, no change from ASC 7 to BNBC. And so there is a line for masonry cantilever shear wall buildings, other masonry shear wall buildings. Most of the time you'll be in this line, all other buildings. So for occupancy category 1 and 2 buildings, standard occupancy and miscellaneous occupancy, 2% of story height, as I said, is the limit on interstory drift. For an assembly building like a school, it is 1.5% of story height. For a hospital, police station, fire station, essential facilities, it's 1% of story height. So this is exactly 1/2 of this limit is exactly 1/2 of what we would allow in an office building, for instance. The top row says buildings less than or equal to 4 stories in height other than masonry, where the non-structural components are designed to accommodate story drift. Okay? Here you get 2.5% of story height. I know a lot of engineers will use that drift limit, claiming that their building has non-structural elements designed to accommodate story drift because they comply with Chapter 13 of ASC 7, which is the chapter on non-structural components. Anyway, it is my advice that you stick to this limit, 2% of story height for standard occupancy buildings, going down to 1% of story height for hospitals. Now, there is a very specific provision that I should draw your attention to. This is the BNBC 2020 section number. For seismic force resisting systems comprised solely of moment frames in seismic design category D, it should be singular category. The allowable story drift for such linear elastic analysis procedure shall not exceed delta sub A divided by rho. So the bottom line is, if the seismic force resisting system consists entirely of moment frames and your seismic design category is D, your drift limit is not delta sub A. It is delta sub A divided by a redundancy factor rho. This redundancy factor rho in AC 7 plays a very, very major role. In AC 7, rho is 1 for seismic design categories B and C, but for seismic design category D, it can be 1 or 1.3. And when we do design load combinations, when we combine seismic load effects with the effects of gravity, the effect of horizontal earthquake forces, E sub H, is amplified by rho. So when rho is 1.3, we are increasing the horizontal earthquake effect by 30%, which is very, very substantial. BNBC 2020 has none of that. We in BNBC do not have the redundancy factor playing any role whatsoever in the design load combinations, and the code does not even talk about redundancy except here, interestingly. Okay, and what it says is rho. The rho is termed as a structural redundancy factor. The value of redundancy factor rho may be considered as 1, with exception of structures of very low level of redundancy where rho may be considered as 1.3. So this is very, very unspecific, and that's all I can tell you. I guess if you want to figure out whether your rho is 1 or 1.3, you will have to fall back on something like AC7. BNBC does not give you any tool. Uh, However, this is if rho is 1.3, this is a very significant reduction in the interstory drift limit. Yeah. BNBC also says for nonlinear time history analysis, which we haven't discussed, this is one of the dynamic analysis methods, the most sophisticated one. The story drift obtained shall not exceed 1.25 times the story drift limit specified above for linear elastic analysis. So because if you base your interstory drifts on nonlinear time history analysis, then the drift limits are relaxed by 25%, which is actually very modest in US practice. The relaxation is quite often quite a bit higher than that. Okay, so that is drift check. A closely related topic is separation between adjacent structures. Separation between adjacent structures. Okay, so buildings shall be protected from earthquake-induced pounding from adjacent structures or between structurally independent units of the same building, maintaining safe distance between such structures as follows. This is a very, very important item. You have to have enough separation between buildings so that the buildings don't hammer against each other, which can cause even collapse, not just damage. So as follows. 1. For buildings or structurally independent units that do not belong to the same property. So, two adjacent buildings, but they're on different properties. There is a property line in between. The distance from the property line to the potential points of impact shall not be less than the computed maximum horizontal displacement of the building at the corresponding level. And this is not the best written, but basically the deflection should not have the building touch the property line. Okay, so the building on this side of the property line can deflect up to the property line. The building on the other side of the property line can deflect up to the property line so that they barely meet but don't really touch each other, or they barely touch but don't do anything more than that. Okay, so the setback distance, as we call it, is equal to the computed deflections. Okay, so number 2, for buildings or structurally independent units belonging to the same property, if the distance between them is not less than the square root of the sum of the squares of the computed maximum horizontal displacements. So when two adjacent buildings are on the same property, the distance between them is allowed to be square root of the sum of the squares of the computed deflections. This is less than what we were talking about above, which is the arithmetic sum of the deflections of the two structures. Okay? In the second case, when the two structures belong to the same property, we allow a shorter separation distance. The idea being that in in the in the second case, when both properties presumably belong to the same owner, we would allow the two buildings to touch, but we do not want unacceptable damage. And it in the judgment of AC 705, if the separation distance is the statistical sum of the computed deflections, then the damage would be not unacceptable. Okay, so if two properties belong to two different owners, we do not we hardly allow the buildings to touch each other. The separation distance now is the arithmetic sum of the computed deflections. If the two buildings belong to the same owner, we would allow a shorter separation distance, which is square root of the sum of the squares of the computed deflections, because now we don't mind the two buildings touching each other, provided the damage is not unacceptable. Okay, so that's what that is, and this is the same as in AC 7. Finally, this is not in AC 7 item number 3, which is, I think, a very good thing that BNBC has added. If floor elevations of the buildings or independent unit under design are the same as those of the adjacent building or unit, the above referred minimum distance may be reduced by a factor of 0.7. So if the floors of two adjacent buildings are aligned, then we would allow a 30% reduction in the separation distance. Yeah. That is a very sensible thing. I thought I put in a picture, okay, in the wrong place. Yeah, this picture should be before the preceding slide. So this 30% reduction in separation distance when the floors are aligned together. I wanted to show you this picture, old picture. This is, I think I took it in Mexico, 1985 is my recollection. So this, and this is a building, this is an adjacent building. The floors are obviously not aligned. The floor is here, the floor is here, with the result that the heavy floor is hammering against the column of the neighboring building. And that is a very bad situation. In this case, there is very major damage. I don't know if you see to the shorter building, the taller building, it is not very visible, but this is a dangerous situation. If the floor hammers against, let us say, the mid height of the column, sooner or later the column is liable to give. If, however, the floors were aligned, this floor were here, then the heavy floor would hit against the heavy floor, which is not the best situation, but that is unlikely to cause unacceptable damage. That is unlikely to cause something like collapse. Okay, so that does justify a decrease in separation distance, and this 30% probably is pretty sensible. So I kind of like this addition that BNBC has made to ASC 705 requirements. Okay, for this is also something very specific in BNBC 2020, although this is in every sensible code and standard you will ever see on seismic design. For structures assigned to design category D, every structural component not included in the seismic force resisting system in the direction under consideration shall be designed to be adequate for gravity load effects, etc. Instead of reading, I will repeat what I said yesterday. Let's take a building frame system, as we called it. Okay. The shear walls carry all the lateral loads, the frames carry all the gravity. Lateral resistance is separated from gravity resistance. The gravity frame is not part of the seismic force resisting system. We have to make sure that the gravity frames will continue to carry full factor gravity loads as they deform together with the seismic force resisting system, the shear walls, all the way up to the design earthquake displacements. This is the deformation compatibility requirement that I was talking about yesterday, and that requirement is stated in this section 2514.4 of BNBC 2020. You can read for yourself. Deformation compatibility is absolutely crucial, but it's not that easy to check. There are intricacies involved that we obviously do not have the luxury of time to get into. Okay, now we are going into a different but very, very important area: earthquake load effects and load combinations. Load combinations themselves we talked about last week. And in the design load combinations, there was earthquake effect E, and we will look deeper and closer into that. Okay, so these are the strength design load combinations of BNBC 2020. Strength design load combinations, 7 of them. It has, in addition to dead load, live load, wind, and earthquake, which are the major loads, if you like, that we always deal with pretty much. We also have F, H, and T, fluid pressure, hydrostatic pressure, and temperature effects. If we strip those other loads, F, H, T, which are typically not there, the design load combinations get reduced to what you see before you. Okay. Now, when it comes to seismic design, we have two load combinations, this one and that one. This is the additive seismic load combination. Gravity effects add to seismic effects. Gravity causes negative bending moment at the support section of a beam. Earthquake also causes negative bending moment. If we want to figure out the largest negative bending moment, we use the additive seismic load combination. This is the counteractive seismic load combination, number 7. Gravity still causes negative bending moment at the support section of our beam, but earthquake has reverse direction. It now causes positive bending moment. If we want to figure out the smallest negative or the largest positive bending moment at our beam support section, we would use the counteractive load combination, 90% dead minus 1.0 E. The plus sign becomes minus. It is the opposite direction of earthquake. Okay. Now, here in the first two lines, I have written the additive and the seismic and the counteractive seismic load combinations. Then the E earthquake effect is made up of two parts: the horizontal earthquake effect and the vertical earthquake effect. In BNBC 2020, it is E sub H and E sub V. E sub H, E sub V. In ASCE 705, E sub H is Q sub E, which are Q sub E, remember, takes a long time. Q sub E, remember, are the bending moment, shear forces, axial forces at the critical sections of various structural members that we obtained by elastically analyzing our structure under the code prescribed seismic forces, which is the design base shear of the code distributed along the height of the structure in the manner prescribed by the code. Remember, for all time, that's what Q sub E is. So ASC 7 tells us the horizontal earthquake effect E sub H is the Q sub E as computed multiplied by the redundancy factor rho that we talked about a minute ago. Rho, as I said, is 1 for seismic design categories A, B, and C in ASC 7, except in Bangladesh, we do not have A. Rho is 1 or 1.3, depending upon what you have in your structure by way of seismic force resisting systems in seismic design categories D, E, and F, except E and F do not exist in Bangladesh. Okay. Now, as I also mentioned a minute ago, in BNBC, you do not have any of this. BNBC, for the purposes of design load combinations, has essentially made rho equal to 1, period. Okay. So in BNBC, E sub H, horizontal earthquake effect, is the same as Q sub E. The vertical earthquake effect, E sub B, ASC 705 says can be taken as 20% of the short period design spectral acceleration, with which we should be familiar by now, multiplied by the design dead load D, 0.2 S sub ds times D. Okay. So in the additive load combination, we write E is equal to rho times Q sub E plus 0.2 S sub ds times D. That would mean vertical earthquake effect acting downward. In the counteractive load combination, we would write E is equal to rho times Q sub E minus 0.2 S sub ds times D, which would mean vertical earthquake effect acting upward. Okay. Now in BNBC 2020, as I said, rho is 1, not mentioned at all. E sub B is given by this expression, 0.5 A sub H times the design dead load D. It doesn't say 0.2 S sub ds times D. BNBC does not. A sub H, it says right there underneath the equation, is equal to 2/3 Z soil factor S times D. So that is equal to 0.5 2/3 Z, remember, is equal to S sub 1, which is 0.4 S sub S. The soil factor S sub BNBC is F sub A of AC 7. The short period design spectral, short period site coefficient, and design dead load remains. So 0.5 2/3 0.4 S sub S times F sub A times D, all of that together gives you 0.2 S sub ds times D. So E sub B of BNBC 2020 is exactly the same as the E sub B of ACE 705. Okay. So in the additive load combination, 1.2 dead, 1.0 earthquake, 0.5 live. In the design load combination, the load factor on live load is shown as 1. But then you remember the exception says unless you are designing a parking structure, a place of public assembly, or an area supporting more than 100 pounds per square foot of live load, your live load factor can be reduced to 0.5. So most of the time we are dealing with a live load factor of 0.5, not 1. So additive load combination, we write E is equal to Q sub E plus 0.2 S sub ds times D. And then if we collect terms, we get 1.2 plus 0.2 S sub ds, all multiplying D, plus Q sub E, plus 0.5 L. In Dhaka, for soil type SD, which is very common, particularly in the north, S sub ds given in Appendix C is 0.45. 0.45 times 0.2 is 0.09. So the load factor of 1.2 on dead load becomes 1.29 on dead load. So by considering vertically downward earthquake effect, we have increased the dead load factor from 1.2 to 1.29. That's precisely what we have done through this, through everything that I have discussed. E is equal to E sub H plus E sub B in the additive load combination, or E is equal to E sub H minus E sub B in the counteractive load combination. Let us look at the counteractive. So 0.9 dead plus 1.0 E. Here E is Q sub E minus 0.2 S sub ds times D. When we collect terms, it's 0.9 minus 0.2 S sub ds multiplying D, then Q sub E. For Dhaka on soft soil SD, S sub ds is 0.45. 0.2 times 0.45 is 0.09. 0.9 minus 0.09 is 0.81. So in the counteractive load combination, we have decreased the dead load factor from 0.9 to 0.81 by considering vertically upward earthquake effect, because that is the conservative thing to do. We are counting on less of the dead load, 81 rather than 90% of the dead load, to counteract the horizontal earthquake effect. Okay, so what I just discussed is extremely important. We do not have fixed dead load factors in seismic load combinations. The dead load factor is increased in the additive load combination by considering vertically downward earthquake effect, and the dead load factor is decreased in the counteractive load combination by considering vertically upward earthquake effect. Okay, then we go to a related but slightly different topic. Load combination with overstrength factor. I'll show you what they are. But before that, ASC 705 requires those load combinations with overstrength factor to be used only in certain specific situations. They are not to be used indiscriminately everywhere, wherever you feel like using them. They must be used where required by ASC 7. They must not be used when not required by ASC 7. The second part is as important as the first part. In seismic design, more is not necessarily better. You cannot just willy-nilly decide to use special load combinations in the design of your favorite structural members. That will get you into trouble. Okay, so use them where required, do not use them where required. The first place, ASC 705 requires the design load combinations with overstrength factors to be used is in the design of foundations of cantilever column systems. You don't even have that in BNBC. The columns like that that are cantilevering from the ground, and that is the seismic force resisting system of the structure. Okay. So foundation and other elements used to provide overturning resistance at the base of cantilever column elements shall have the strength to resist, etc. So let us not spend time on that because you do not really have it in BNBC. The second is much more important. These things are everywhere. Elements supporting discontinuous walls or frames. So the thousands of residential buildings where people park their cars underneath the apartment building, all of them have columns supporting supporting walls. And that is a situation where the column supporting the discontinued shear walls must be designed using load combinations with overstrength factor. So this is a huge area that uh, we will likely discuss more than once, but those columns are a prime candidate for design using load combinations with overstrength factor. This is a by now famous picture. This was the Olive View Memorial Hospital after the 1971 San Fernando earthquake. You see the bottom story has columns, and then the shear walls start. Okay? Those columns back in those days where there was no difference between a California column and a Chicago column. There is plenty of longitudinal reinforcement, hardly any transverse reinforcement. Tie spacing was 12 or 14 inches, no 135-degree hooks, no cross ties. The building is standing up only because, for reasons unknown to me, those central columns are spirally reinforced columns and the pitch of the spiral is very tight. So those columns are in good shape, except the cover has fallen and they are holding the building up. If all the columns were like that, the building would have been down on the ground. Okay. So columns supporting discontinuous stiff elements, those columns today would have to be designed using load combinations with overstrength factor. No questions about them. The columns have to be stronger. In addition, they have to be much more ductile, which is a different story. Yeah. So first situation is foundations of cantilever columns. Second is columns supporting discontinued stiff elements. The third situation where ASC 705 requires the overstrength load combinations to be used is in the design of collector elements of uh, diaphragms. Okay, what is a collector element? So this is a diaphragm, a slab bending in its own plane under inertia forces caused by earthquakes. It could be lateral forces due to wind, doesn't make any difference. In plane bending of the slab is what is connoted by diaphragm action. Now, this diaphragm under that lateral load develops shear forces along the parallel edges. Okay, this face develops tension, that face develops compression, and the parallel faces develop shear. If the entire width of the diaphragm, let us say 50 feet, were supported by shear walls or frames, the shear would have been directly transferred to the supporting shear wall or frame, and there would be no question of a collector. But if the situation is as shown in the picture, you have 50 feet of diaphragm edge and 20 feet of shear walls, there has to be a beam-like element collecting the shear forces and then delivering them to the shear wall. It can be a beam that is a physical beam, or it can be a bunch of reinforcing bars. Whichever way, you have to have an element that is collecting the shears developing at the edge of the shear wall and then eventually delivering them to the supporting shear wall. So that element would be a collector element, and that collector element has to be designed using load combinations with overstrength factor. Why? It is explained here. This is a parking structure on the uh, this was part of the Northridge Fashion Center, as they called it, a shopping center very close to the epicenter of the 1994 Northridge earthquake in the Los Angeles area of California. The parking structure is essentially down on the ground, or much of it is. However, as we approached the parking structure, this shear wall at the front was not only standing, it looked surprisingly good. Nothing had happened to it, not even cracking. And the question naturally arose, how come it looks so good? You know, everything else around it is down on the ground, and this thing is standing up in all its glory, looking like nothing has happened to it. And the reason became apparent pretty quickly. The shear wall looked that good because it didn't have to do anything through the earthquake. The collector elements that were supposed to take forces to the shear wall that would have made it work failed before the force transfer took place. Okay. And if you don't have to do anything, it is easy to look good. All of us know that. Okay. So that was the lesson that was learned, that the collectors have to be stronger than the shear walls to which the loads collector forces have to be transferred. So that's what led to the requirement that collector elements of diaphragm shall be designed using load combinations with overstrength factor. These are the load combinations with overstrength factor. This is the additive load combination. This is the counteractive load combination. In regular strength design load combination, ASC 705 uses rho times Q sub E. BNBC uses just Q sub E. In the load combination with overstrength factor, the Q sub E is amplified by the overstrength factor omega sub 0, which is listed in the R values table, table 12.2-1 of ASC 7. Okay, omega sub 0 for a special moment frame is 3. So we are looking at a significant number. It can be 1.5, 2, 2.5, 3, something of that magnitude. Okay. So load combinations with overstrength factor. BNBC tells you where to use those load combinations in section 25561. Okay. The first item that BNBC mentions are columns, beam, trusses. These are the columns supporting discontinued shear walls that I was talking about. It is not just columns. Any structural member supporting a discontinued stiff element. That is the most general way of looking at it. So that is item number 1 in BNBC. Item number 2 has item number 2 is essentially misplaced. It talks about 25% increase in the design forces for certain diaphragm elements that we will look repeatedly at when we go to our discussion on structural irregularity. Okay, so they put it in here for reasons unknown to me. This is not application of load combination with overstrength factor. The third item is the collector elements of diaphragms, collector elements, any splices in the collector elements. In concrete, collector element splices would be uncommon, but if the collector elements are made of wood, for instance, splices are very, very common. and the connections of the collector elements to resisting elements like shear walls. The collectors and their connections have to be designed using load combinations with overstrain factor. Finally, an item that is not in AC7 but in the IBC batter piles, which are the inclined piles. Batter piles and their connections shall be capable of resisting forces, moments, etc. So those have to be designed using load combinations with overstrain factor, batter piles and their connections. Okay, so that brings me to the discussion of structural irregularity. This was part 3 yesterday. I showed you the uh, the essentially the descriptions in AC 705 and BNBC 2020 and said that any discussion will be postponed until today. So a table of what used to be called plan irregularities, and it is still called plan irregularities in BNBC. We now call them horizontal irregularities. And a table of vertical irregularities, as I said yesterday, started in the 1988 edition of ACE of the Uniform Building Code, UBC, long time ago. And those tables have undergone surprisingly small changes in all the ensuing years. These have been a durable part of the code that have proven to be very useful. The table of horizontal irregularities have 5 categories of horizontal irregularity: torsional, re-entrant corners, diaphragm discontinuity, out of plane offset of the seismic force resisting system, non-parallel seismic force resisting systems. The first one, torsional irregularity, at one point in 2000 IBC was split into torsional and extreme torsional, and we will look at the definitions. The definitions are contained in section 2553 of BNBC 2020. Now, so 2553 is part of part 6, chapter 2 of BNBC. I found that in part 6, chapter 1, there are also tables of structural irregularities. And I do not understand it, first of all. Secondly, it's a very bad practice to have the same thing said twice in the same document, because if if not, if the when something is repeated, if it is not repeated exactly as it was in the first place, then there can be confusion on the part of the user, understandable confusion, which one is right. Two different things are said in two different places. So it's generally a very bad practice. Why it has been done, I do not know. But in any case, so the definitions of plan irregularities are in section 25531. So you see torsional irregularity, re-entrant corners. I wouldn't go into them now. I have much more discussion coming up. So we will discuss the definitions, but with pictures and things. Diaphragm discontinuity, out of plane offsets, non-parallel systems. Yeah. I will only say that the definitions are essentially the same as those in AC 705. Really no change. Vertical irregularities, this is another table 1232 of ASC 705. There are also 5 categories. Stiffness irregularity, also called soft story irregularity. Weight or mass irregularity. Vertical geometric irregularity. In-plane discontinuity. This is now in-plane as opposed to out-of-plane discontinuity in vertical lateral force resisting elements, and discontinuity in lateral strength, also called weak story. Okay. Now, along the way, the soft story irregularity was split into 2 parts: soft story and extreme soft story. And similarly, weak story irregularity also was split into weak story and extreme weak story. The definitions are given also in 2553. This is now 25532, vertical irregularity. The soft story definition is the same as in ASC 705. The mass irregularity definition is the same as in ASC 705. The vertical geometric irregularity, BNBC has altered the ASC 7 definition, and we will look at both. Vertical in-plane discontinuity in vertical elements of the seismic force resisting system, that definition also has been altered in BNBC 2020. The vertical type 4 is a bit different. And then actually what BNBC has is an older version, is what we used to have. Now in AC 7, already in O5, it has changed. This one is completely a BNBC creation, the type 3. And then weak story definition is the same as in AC 705. So in the remainder of this segment on irregularity, this is what I plan to do. Earthquake experience with irregular structures. I want to take you through very briefly a few case histories, if you like. Horizontal structural irregularities and vertical, one after another, we will discuss. So this structural irregularity discussion starts with configuration, structural configuration. The word, if you look it up in the dictionary, says relative arrangement of parts. Relative arrangement of parts. Something produced by such arrangement of parts. Okay, that's configuration. For our purposes, we talk about horizontal or plan configuration, how parts are arranged in plan. And then vertical configuration, how parts or structural members are arranged along the height of a building. Okay, both are of concern to us as structural engineers. The configuration of a structure can significantly affect its performance during a strong earthquake that produces the ground motion contemplated in IBC AC 7 or BNBC 2020. I showed you this building out of Mexico City, 1985 earthquake. The building housed telecommunication equipment, and the damage to the building meant that Mexico was cut off from the rest of the world for quite a while. The main thing wrong with the building was it was in the wrong height range. The predominant period of ground motion in downtown Mexico City locations was about 2 seconds. This building had period that lengthened into 2 seconds, and that was the major factor behind the damage that you see. But the L shape of the building also contributed to its problems. There is absolutely no question about it. If it were a rectangular block, it can be speculated that the performance would have been substantially better. Okay? So the configuration matters. AC7 seismic design provisions were developed basically for regular buildings. You have to understand that. What we see now today, whether you look at BNBC, AC7, IBC, has been evolving since, to my knowledge, since the 30s. It probably started a bit earlier, and uh, I haven't paid that much of attention, but definitely since the 30s, I am personally aware of how things have evolved. Okay, and all of that evolution considered basically only regular buildings. Irregular buildings started attracting attention with the 1988 UBC, which is not yesterday, so some time ago. But the fact remains that the the basics of seismic design have always considered only regular buildings. Past earthquakes have repeatedly shown that irregular buildings suffer greater damage than regular buildings, incomparably greater damage. I have been to plenty to tell you firsthand that it is incomparable. It's earthquakes have an uncanny ability to seek out weaknesses in buildings, and structural irregularity is one of those weaknesses. Okay? Uh, unless you have properly designed to account for the irregularity, which can be done. And, and this greater damage to irregular buildings happens even with good design and construction. Okay? So, good design and construction. I just said that you can design to have irregularity in your building, but it has to be properly done. Okay, just regular good design it will not suffice. Okay, a few examples. The This is Marina district of San Francisco. After the 1989 so-called Loma Prieta earthquake, it was not a big earthquake, as I mentioned one of these days, a week or two ago. This part of San Francisco, this is a pretty fancy residential district, is entirely built on fill. 1906, there was a big earthquake, and the rubble and so forth from that earthquake was used to fill part of the bay, and that's where the district grew up. Now, when these buildings were built, the buildings that you see, there were no automobiles. People had carriages and horses. When the automobile came, people cut openings in the ground levels of their buildings to create garages. And that resulted in soft stories. The ground story now had much smaller stiffness than the upper stories. And as a result, one building after another in the Marina district had problems, serious problems. Okay? This is a closer up view of so this garage was created, or this one, all the same. All the buildings had the same thing. This opening was cut in what used to be a shear wall, and now we have only the two pilasters or columns instead of a shear wall, and that is the reason why the buildings have major problem. The Olive View Memorial Hospital after 1971 San Fernando earthquake. I showed you a picture already from this face of the building. This is the front of the building. This canopy or roof over columns. The ambulances were all parked underneath this roof. This was a roof on in wind design. This should be an open structure. Okay, columns holding up this roof. This is also a cantilever column system that is not mentioned in BNBC 2020. Anyway, the uh, canopy has not entirely collapsed, but some of the columns have collapsed. So the ambulances underneath are pinned there. They cannot move and they're stuck. And when ambulances don't function, a hospital they cannot do much business. So the hospital itself is standing up, uh, and standing up because of the factor that I mentioned already. But this very fact that the cantilever column system failed made the hospital non-functional. This picture I have gone through, so let me not spend more time. A Filipino earthquake, 1976 in Manila. The building is at the intersection of two streets. So there are two street fronts, and it is a natural desire for. So typically, you would have shear walls on the left face of this kind of a building on the back face, but on the street facing faces, there would be no shear walls, okay, for obvious reasons. And that means significant torsion. And because of the torsion, the ground story has failed. The building, at least in these parts, is one story shorter than it was before the earthquake. Okay? So torsional irregularity is a problem. This is another building at the corner of two streets, except this is a triangular building. There's only one back face. One back face and then two street facing faces. The back face, the one face that doesn't face the street has shear walls, but the other two faces have no shear walls, with the result that the building has done extremely poorly. Actually, the picture does not show you everything that has happened to the building. This was Mexico 1985. It could be pretty much anywhere else. So reasons for poor seismic performance for irregular structures. In a regular structure, inelastic demands produced by strong ground shaking tend to be well distributed throughout the structure, resulting in a dispersion of energy dissipation and damage. In irregular structures, inelastic behavior can concentrate in the zone of irregularity, resulting in rapid failure of structural elements in these areas. So it is the uneven distribution of inelastic displacements that is the problem with irregular structures. Some irregularities introduce unanticipated stresses into the structure, which designers frequently overlook when detailing the structural system. You see the picture to the left. It is pretty descriptive. Elastic analysis methods, this is very important, typically employed in structural design, often cannot predict the distribution of earthquake demands in an irregular structure very well, leading to inadequate design in the zone of irregularity. This is elastic versus inelastic. This is not static versus dynamic. And what we are saying there, this I think maybe even common sense. So take this building. The left face has shear walls, the back face has shear walls, the front faces do not have any shear walls. So earthquake forces will gravitate to the strong elements, which are the shear walls. So those shear walls at some stage will begin to yield. Okay, that goes without saying. And when the shear was begin to yield, the loads transfer from those yielding elements to the frames. And you will not capture that out of elastic analysis. There is no way. Okay, so that's what we are trying to say on the slides that I was on. So elastic analysis methods typically employed in structural design often cannot predict the distribution of earthquake demands in an irregular structure very well, leading to inadequate design in the zone of irregularity. Okay, now we come to code regulations introduced in 1988 UBC, evolved since then. Thrust, this is important. Thrust is to encourage that buildings be designed to have regular configurations. We are not really, our preference is that you stay away from irregularity, not that we design for irregularity. Okay. Important features is prohibition of gross irregularity in buildings located on sites close to major faults where very strong ground motion and extreme inelastic demands can be experienced. Okay. This is mostly not a problem in Bangladesh. You do not have high ground motion. You are not close to major faults, not uncomfortably close. But in any way, AC 705 actually prohibits some structures with some irregularities close to major faults that can generate large earthquakes. You have already seen this horizontal irregularities, AC 705, vertical irregularities. Uh, I hesitated, but then I kept this in. We create at our company SKJ these so-called code masters. These are laminated 4 or 6 page affairs where we uh, give you how to do something like seismic design step by step. In this code master, seismic design, I believe, is in 10 steps. And this one is to 20 is for AC 705 and 2006 IBC. This is why I pictured it here. Uh, the document has been updated with every edition of the IBC. Uh, the what I did want to show you is in this 6 page affair, you see how much space we have devoted to a discussion of structural irregularities. That's how important we think the topic is. Seismic analysis procedures we talked about yesterday. We have simplified analysis that you don't have in BNBC, which is well and good. Equivalent lateral force procedure, then the dynamic analysis procedures, modal response spectrum, linear response history analysis, nonlinear response history analysis. I showed you a version of this chart yesterday. When is the equivalent lateral force procedure permitted, and when do we have to, when will the code force us to do dynamic analysis? Okay, I went over this yesterday. The important thing is, if you have, so seismic design categories B and C, dynamic analysis is never required. Design categories D, E, and F, if it is a tall building more than 160 feet of height, ASC 705 will allow equivalent lateral force procedure only if the structure has no irregularity and if the period is less than 3.5 times the transition period, which is about half a second. So we are talking about a period threshold of 1.75 seconds or so. In BNBC, you will be allowed to use equivalent lateral force procedure if your period is less than 4 times the transition period T sub S, which is T sub C in BNBC. or 2 seconds, whichever is the smaller of the two. Okay? It doesn't mention structural regularity or irregularity. In AC 705, for shorter buildings up to 160 feet of height, you have to do dynamic analysis if your structure has certain quote unquote bad irregularities, which would be horizontal 1A, 1B, torsional, extreme torsional, a vertical 1A, 1B, which would be substory, extreme substory, and then vertical 2 and 3, and those will come up. So this I already went over. If a building seismic design category D and above has a period larger than or equal to 3.5 times T sub S, then dynamic analysis procedure must be used. In B and BC, it is T larger than or equal to 4 times T sub S or larger than or equal to 2 seconds, whichever is the smaller of the two. Okay, now I will take the horizontal irregularities one at a time and share with you what it is that we are required to do in design. So this is the actual table of horizontal irregularities in ASC 705. These are the descriptions of the different types, 1A, 1B, etc. This is the most important column. AC7 tells you if you have torsional irregularity or horizontal irregularity type 1A, you have to comply with all those sections in AC705. Okay, very direct. So you have this problem, you have to comply with all those requirements. If you have diaphragm discontinuity irregularity, you have to comply with those requirements, only 2 as opposed to 6 here. Okay, so we are told exactly what we have to do, and this is what I want to take a look at with you. In BNBC 2020, as I said, the comparable table is in chapter 1, not in chapter 2 or part 6. And this is the table. We have the descriptions as in ASC 7, then also as in ASC 7 a reference section number, but this is kind of different because the 2.5.5 to 2.5.14 is almost the entirety of the seismic design provisions, much of it. So I do not know that is all that terribly meaningful. But 1738, and later you will see when we come to vertical irregularities, there is another section that is referenced that is kind of meaningful. The 1738 section that is referenced here, when you have torsional, actually many, horizontal type 1, type 2, type 3, type 4, for all of those 1738 is invoked. What does 1738 tell you? So this is the section. The relevant part of the section says for structures assigned to seismic design category D, having a plan irregularity type 1, 2, 3, or 4, a vertical structural irregularity type 4, the design forces determined from section 257 shall be increased 25% for connections of diaphragms to vertical elements and to collectors, and for connections of collectors to vertical elements. So, design forces shall be increased 25% for connections of diaphragms to vertical elements and to collectors. So the diaphragm to vertical element, diaphragm to shear wall connection, diaphragm to collector connection, and for connection of collector to the vertical element. This is the collector to shear wall connection. Okay, for all of those, 25% increase in design forces. So this is where you saw the same thing in the section where I said this is misplaced. I think here it is kind of correctly placed. Collectors and their connections also shall be designed for these increased forces, 25% increase, collectors and their connections, unless they are designed for load combinations with overstrength. Okay, this is exactly how ASC 705 does it also. Okay, high seismic design category, we will have to design for load combinations with overstrength, otherwise 25% increase. For structures having plan irregularity type 2, that's extreme torsional, diaphragm cords and collectors shall be designed considering independent movement. No, type 2 is re-entrant corner. So for structures having a plan irregularity type 2, re-entrant corner, diaphragm cords and collectors shall be designed considering independent movement of any projecting wing of the structure. Each of these diaphragm elements shall be designed for the more severe of the following cases: motion of the projecting wings in the same direction, moving towards each other, and the projecting wings going apart from each other. Okay, so this is said. How to exactly do it is not that clear or that simple, but anyway, that's that is the 1738 that is invoked from the table of plan irregularities in BNBC part 6 chapter 1. Okay, let's get into the definition of torsional irregularity for the first time. So this building has deformed because of torsion, the deflection. So it has deflected and it has also rotated because of torsion. The deflection here, the minimum deflection and the maximum deflection are very different. If the average deflection, if the maximum deflection is less than or equal to 120% of the average, then we have no torsional irregularity. It is always, the definition is always in terms of the threshold. Up to 20%, we say, don't worry, we don't have any irregularity. If the ratio of maximum to average is more than 120%, less than or equal to 140%, we have type 1A, torsional irregularity. If the maximum is larger than 140% of average, then we have an extreme torsional irregularity, extreme 1A. Okay? Now, in calculating this delta maximum and delta average, we have to include accidental torsion, but no amplification of accidental torsion. This is another picture saying exactly the same thing. Okay, delta A is the maximum deflection, delta B is the minimum, average is delta sub A plus delta sub B divided by 2. If the maximum is larger than 1.2 times the average, we have a torsional irregularity type. That's type 1A, torsional, not extreme torsional. Okay. Now, if we have torsional irregularity, ASC 705 invokes all those sections of ASC 7, and we will take a look at those. First one is 25% increase in seismic forces in connections in diaphragms and collectors, something that we just went over. It is also in 25562, chapter 2 of ASC 7. Of BNBC. Okay, so in BNBC it is in two places, 17738 or whatever the section that we read, and in 25562 same thing is said. 25% increase in seismic forces in connections and diaphragms. Okay, then okay, I think the easiest thing will be to keep on coming back to this table. So let's take a look at the first one. Increase in forces due to irregularities. Okay. So for structures assigned to design categories D, E, and F, this is AC7, having horizontal type 1A, 1B, 2, 3, or 4, or vertical type 4. The design forces determined from section such and such shall be increased 25% for the following elements of the seismic force resisting system. Connections of diaphragms to vertical elements and to collectors and their connections, including connections to vertical elements of the site. This is word for word the same as in BNBC 2020, the language that I read. So everything is pointing to the same direction. And I have given you pictures to explain this diaphragm to collector connection and the collector to shear wall connection. So we are talking about three connections: diaphragm to shear wall, diaphragm to collector, and collector to shear wall. Okay, and all of this is illustrated in these pictures, very, very clearly illustrated. So the first requirement, 25% increase, I think should be abundantly clear. Then we are asked to go to the table of permitted lateral force resisting systems. Permitted analysis procedures. Okay, so if you go to that table of permitted analysis procedures, you will see that whenever you have a torsional irregularity 1A or 1B, even for shorter buildings, you will have to do dynamic analysis. Okay, so that's what the second reference. Going back and forth is somehow not that simple. Okay, so if you go to that table, you will see that according to ASC 705, equivalent lateral force is prohibited. However, it is not prohibited in BNBC. BNBC will have you do dynamic analysis whenever you have a vertical irregularity, but horizontal irregularity does not keep you from doing equivalent lateral force procedure. Okay, so this is different between the two documents. Then 1273, this column tells you where the restriction applies, design category B through F. 3D structural model required. If you have torsional irregularity, I think it is almost common sense that you will need a 3D model. I said it is not explicitly said in BNBC 2020, but I'm not sure. I may have missed it. It may be said there. In any case, you need 3D, whether it's explicitly said or not. Torsional irregularity, you cannot do a 2D analysis. Doesn't make any sense. Next section, amplification of accidental torsion. This is section 12843 of AC 725.762 of BNBC 2020. We will take a look at that. We will take a look. The next thing is design story drift based on largest difference in deflection. We will take a look at that also. So both of those requirements are in both documents. And finally, 3D structural model required in nonlinear response history analysis. I do not believe it is explicitly stated in BNBC, but it doesn't make any difference. Okay, so amplification of accidental torsion and design story drift, we will take a look at those without coming back to this table. Okay, so amplification of accidental torsion is the topic. This picture I showed you yesterday, when we are considering how the story shear is distributed among the two frames and the three shear walls. I mentioned that because the shear wall is longer than that shear wall, the center of rigidity is at an eccentricity from the center of mass, and that causes torsion. This is actual or inherent torsion. Accidental torsion is where the two centers coincide, so we have no actual torsion, but we still consider a torsion called accidental torsion, that is the story shear multiplied by 5% of the plane dimension perpendicular to the story shear. Okay. We must design these days for the actual torsion plus the accidental torsion. And if we have torsional irregularity, 1A or 1B doesn't make any difference. The accidental torsion has to be amplified by an amplification factor up to 3 before adding to the inherent torsion. I told you all of this yesterday. Now, torsion is a consideration if your diaphragm is rigid. If the diaphragm is flexible, it cannot transmit any torsion, and then it is not an issue as far as what we are discussing. So for structures assigned to design category C, D, E, and F, forget about E and F in your case, but C and D, amplification of accidental torsion. Without flexible diaphragm, with horizontal irregularity 1A, 1B, okay, the accidental torsion at each floor level needs to be amplified by a factor A sub x up to 3, where A sub x is the maximum deflection divided by 120% of the average deflection. So same picture as before. This is maximum, this is minimum. Average is delta sub A plus delta sub B by 2. The the torsion, accidental torsion amplification factor A sub x is the maximum torsion divided by 120%, not maximum torsion, the maximum deflection divided by 120% of the average deflection, the ratio squared, that is A sub x, and it is up to 3. Where torsional irregularity exists for seismic design category C or D, the irregularity effect shall be accounted for by increasing the accidental torsion at each level by a torsional amplification factor A sub x, as illustrated, etc. Okay. So that's amplification of accidental torsion required when you have type 1A or 1B irregularity, horizontal. The second is the how we compute interstory drift. For structures assigned to design category CD, having horizontal irregularity type 1A, 1B, the design story drift shall be computed as the largest difference of the deflections of vertically aligned points at the top and bottom of the story under consideration along any edges of the structure. If we don't have torsional irregularity, we compute the deflections at the various floor levels at the center of mass. So torsion is not part of the picture. Torsion does not contribute to the calculated deflection. But if we have torsional irregularity, then the contribution of torsion to deflection has to be considered. This is why we take vertically aligned points along the edges of the building. Okay, so this is a requirement, and theoretically you have to go around the perimeter figuring out the largest difference. but most of the time by inspection, we know where the area where the largest difference is likely to be, and that's where we concentrate. So from torsional to extreme torsional, 1B. So now the maximum is larger than 140% of average. This irregularity, AC 705, a building with this irregularity will be prohibited from being designed and built, where S sub 1, the mapped long period spectral acceleration, is larger than or equal to 75% of G. That can happen only in the vicinity of known faults that can generate large earthquakes. In Bangladesh, you simply do not have that. There is no S sub 1 larger than 75% of G. So you do not have this prohibition. Okay. 1A to, we are going to 1B. The same restrictions as for 1A. It is identically the same table. Okay. So I do not believe that we need to discuss anything in particular. Okay. Then horizontal type 2, re-entrant corners. If this projection B is more than 15% of A, this is A, this is B. If B is more than 15% of A and this D is more than 15% of C, then we have a re-entrant corner irregularity, horizontal type 2. Now there are two uh, uh, items in AC 705 that are triggered, that are invoked. One requires 25% increase in seismic forces in connections in diaphragms and collectors. This is BNBC section 25562, no difference between the two documents. And the other is the table of permitted analytical procedure. If you go there, the equivalent lateral force procedure is permitted both by ASC 705 and by BNBC 2020. Okay, there is no prohibition. Horizontal type 2, re-entrant corner. We are still on the same topic. Re-entrant corners may form coupled wings, which may respond in an opening and closing fashion. Remember, BNBC specifically talks about this. This may give rise to high stresses in the vicinity of re-entrant corners. Okay. Horizontal type 3, diaphragm discontinuity irregularity. Diaphragm discontinuity exists when area of opening in the diaphragm is larger than 50% of A times B, the diaphragm area. So if the opening area is more than 50% of the area of the diaphragm, or effective diaphragm stiffness changes more than 50% from one story to the next. Either case, you have a diaphragm discontinuity irregularity. The first one is pretty clear and unambiguous. The second one has been somewhat problematic over the years because this effective diaphragm stiffness is not defined. And secondly, the 50% change sometimes is kind of, I don't want to say automatic. In this country, office buildings are typically made of steel. So steel frames with steel decks, metal decks. The metal decks are all topped with concrete in the floors, but the roof metal deck is almost never topped. So the roof is untopped, the floors are topped. So between the top floor and the roof, there is always a 50% difference. Are all of those buildings, do all of those buildings have diaphragm discontinuity irregularity? That has been a controversial topic. In any case, so if you have a diaphragm uh, discontinuity, this is type 3 horizontal, then the two requirements that are invoked are the 25% increase in seismic design forces and permitted analytical procedure. If you go there, there is really no restriction. Equivalent lateral force is permitted. So it is permitted in ASC 705 as well as in BNBC 2020. BNBC, as you recall, will force you to do dynamic analysis only for vertically irregular structures, not for horizontally irregular. The diaphragm discontinuity, the stiffness of the diaphragm changing 50% from one level to another. This is pretty automatic. In the US now, what you see in the picture is very common. Residential buildings are now up to 5 stories tall, made of wood, supported on a concrete podium, although the podium could be concrete block masonry also. So this diaphragm is made of concrete, the first suspended floor. After that, those are wood diaphragms. And a 50% differential is almost guaranteed. So this is a question we have gotten many times. If the roof diaphragm has an opening in it, which results in the stiffness of the second floor diaphragm being 50% stiffer than the roof, does that make it irregular? The plan irregularity definition says story to story. Yes, it would be considered irregular, doesn't matter if floor or roof. So in the definition of this particular type of irregularity, there is no distinction between the roof and the floor, unfortunately. So there is no question that is the case. Okay. Horizontal type 4, out of plane offset of seismic force resisting system. So this shear wall coming down and then it is supported on column or another shear wall, but there is an offset. This shear wall is coming down and then it makes an offset and goes down those lines. Okay. So out of plane offset. This is a better picture from PIMA. Okay, this shear wall was coming down and then it is supported on a transfer slab, as we call it, and then the shear wall goes down another line. These things are pretty common in practice. This is an actual residential building. This is a shear wall, and then the continuation of the shear wall is here. Okay? So this is a pretty significant out of plane offset. So in this case, there are a lot of requirements, as you see. The columns supporting discontinued shear walls have to be designed for overstrength, as we have discussed earlier. The 25% increase in seismic forces in connections in diaphragms and collectors, that gets invoked. Permitted analytical procedures. ASC 705 will permit equivalent lateral force procedures, so will BNBC 2020. 3D structural model required by ASC 705. That is not explicit in BNBC 2020, but it should be very much encouraged. Finally, 3D structural model required in nonlinear response history procedure. I do not expect that too many of you will do that, but in any case. So I would say that this is very significant, very important, and then the rest of them are definitely not unimportant. The final horizontal irregularity type 5 is non-parallel seismic force resisting systems. Okay? And this is a San Diego building that is almost uh, a direct translation of this plant shape. Now, the definition says non-parallel system irregularity exists when the vertical lateral force resisting elements are not parallel to or symmetric about the major orthogonal axis of the seismic force resisting system. Are not parallel to makes a lot of sense. Not symmetric about does really not make any sense. And that was deleted from AC7 a long time ago. Even in AC705, it is gone. The symmetric about. So I would strongly urge you to forget about the symmetric part. Anytime you have shear walls or resisting systems that are not parallel to the orthogonal axis, non when vertical lateral force resisting elements are not parallel to the major orthogonal axis. Whenever they are non-parallel, you have type 5 irregularity. So if you have type 5 horizontal design categories C and above, we have to consider the fact that earthquakes can hit from any old direction. They are not constrained to hit your structure along the orthogonal plane axis. So we have to do what is called orthogonal load combination. We'll take a look at that. Then permitted analytical procedure, equivalent lateral force is permitted by both documents, ASC 705 and BNBC. The 3D structural model required not explicit in BNBC, and the same thing is true of 3D structural model in nonlinear time history analysis. Now, these orthogonal effects or direction of loading, which must be a consideration when you have type 5 horizontal irregularity. Okay? So if your design category is B, the design seismic forces are permitted to be applied independently in each of two orthogonal directions, and orthogonal interaction effects are permitted to be neglected. ASC 7 says that, BNBC also says that. So if your design category is B, you are home free. You do not have to consider orthogonal effects. Design category C, structures that have horizontal irregularity type 5 shall use one of the following procedures. Now you have to consider orthogonal effects, and one way to do that is orthogonal combination procedure. You do equivalent lateral force modal response spectrum or linear response history analysis with loading applied independently in any two orthogonal directions, and then you design a structural member for 100% of the effect of the X earthquake plus 30% of the effect of the Y earthquake, or 30% of the effect of the X earthquake and 100% of the effect of the Y earthquake, whichever is the larger of the two. If 100% of X plus 30% of Y is larger than 30% of X and 100% of Y, then you design for 100% of X plus 30% of Y. So how does it work? So we have this structure, obviously, this shear wall and that shear wall are not parallel to that axis, so we have type 5 irregularity. Okay. This is earthquake X, this is earthquake Y. Earthquake X causes V sub x1 in shear wall 1, V sub x2 in shear wall 2, V sub x3 in shear wall 3, V sub x4 in shear wall 4. Earthquake y causes V sub y1, V sub y2, V sub y3, V sub y4. So 100 plus 30 would mean 100 of x plus 30 of y would mean V sub x1 plus 30 of V sub y1, V sub x2 plus 30 of V sub y2, and so forth. 100% of y and 30% of x would mean 30 of V sub x1 plus 100 of V sub y1, and so forth. Whichever is the worst of the two, whichever of those two shears is larger, is what you should design that particular shear wall for. That's the idea behind this 100% plus 30%. Okay. When we have two columns, not two columns, when you have a column that is part of two orthogonal seismic force resisting systems, okay, you have to design the column for 100% of the X earthquake plus 30% of the Y earthquake, or the other way around. Okay. So the X earthquake will cause P sub X axial load, M sub X bending moment about the Y axis, and M sub Y bending moment about the X axis. So we'll take, okay, the Y earthquake will cause P sub Y axial load, M sub Y bending moment about the Y axis, and sorry. So M sub X is bending moment caused by the X earthquake. M sub Y is bending moment caused by the Y earthquake. Now, when we say 100% plus 30% for this column, 100% of the effect of X earthquake and 30% of the effect of Y earthquake, the axial forces are additive. We take 100% of the axial force caused by X earthquake, add it arithmetically to 30% of the axial force caused by the Y earthquake. That part is simple. But the bending moments are orthogonal to each other. So we are now talking about biaxial bending. We have to design for 100% of M sub X plus 30% of M sub Y, or 100% of M sub Y plus 30% of M sub X. This combination will go with that axial load, and this combination, 100% of X moment and 30% of Y moment, will go with that axial load. And just by looking, we do not know which one is more critical. So we have to find out by going further into design which of those orthogonal combinations governs our design. So that was one way, 100% plus 30%. The other is simultaneous application of orthogonal ground motion, linear or nonlinear response history analysis with orthogonal pairs of ground motion acceleration histories applied simultaneously. You hit the building simultaneously with X earthquake and Y earthquake. Obviously, the earthquake ground, the acceleration histories are digitized, and then you do your dynamic analysis under the two earthquakes applied simultaneously. That is direct way of considering orthogonal effects. Okay, vertical irregularities, stiffness. So we will take 1A first, soft story. The vertical irregularity table is in chapter 1. No, this is the AC7 table. Okay, same as the horizontal table. The definitions are here. These are the sections of AC7 that are invoked, and those are the applicability of those requirements, design categories D, E, and F. So this is a pretty comprehensive table. Comparable table in B and BC is in chapter 1, part 6. Now, in addition to 1738 and all those sections, there is a section 2517 that is invoked. Okay, and 2517 is a section entitled Buildings with Soft Stories. And the way time is running, I think I probably will not go into the substance of these. I think, well, let me read the first part. So, buildings with possible story drift action at ground level for providing open parking spaces belong to structures with major vertical irregularity. Special arrangement is needed to increase the lateral strength and stiffness of the soft or open story. The following two approaches may be considered. Anyway, you can read that. So this is a specific section in BNBC 2020 that is invoked when you have type 1A or type 1B vertical irregularity. Okay, this section 2517. So I did want to point that out. I read that the only reason I hesitate to go into this is it is not that straightforward, and I am not sure how easily doable the suggestions are. Okay, so this is vertical type 1, soft story irregularity. Soft story stiffness less than 70% of the story stiffness above, or 80% of the average story stiffness of the 3 stories above. Now, I absolutely want to emphasize that a soft story does not have to be at the bottom of the structure. It can be anywhere of the height of the structure. And this is a very, very good example of that. I think I showed you that the day I was talking about earthquake experience. This is the City Hall of Kobe. The bottom part of the structure has steel reinforced concrete. The concrete has steel shapes concealed within them. But at that level, the steel shapes were discontinued, giving us a stiffness discontinuity, and that is the level that failed. Okay, the stiffness was lower than the stiffness decreased all of a sudden. So the definition is here, and the thing to emphasize is that a soft story does not have to be at the bottom. It's not at all always the case. Okay, the restriction that is invoked is that you have to do dynamic analysis. Neither AC7 nor BNBC 2020 will permit equivalent lateral force procedure for a building with soft story irregularity. Extreme soft story stiffness is less than 60% of the story stiffness above. And so the regular soft story, it is 70% and 80% of average. The 70 goes down to 60 for extreme soft story, or 70 rather than 80% of average story stiffness of the 3 stories above. Okay, so this is extreme soft story. This is prohibited in design categories E and F. E and F do not exist in Bangladesh, so you do not have a prohibition. But the AC 705 prohibition tells you that this is not an irregularity that we encourage. So we go from soft story to extreme soft story. The restriction does not change. All we are required by AC 7 to do, other than the prohibition in ENF, is dynamic analysis. Okay, that's all we can do. The weight or mass irregularity. Story mass larger than 150% of adjacent story mass. Here, in this case, Unlike in case of diaphragm discontinuity, irregularity, roof that is lighter than the floor below need not be considered. So there is an exemption for the roof. But otherwise, story mass larger than 150% of adjacent story mass will give you this weight or mass irregularity. And here also, what will be required to do is dynamic analysis rather than equivalent lateral force procedure. That is the only restriction imposed on us if we have a mass irregularity. Now, this is something I kept in, but I will not spend your time on because you do not have it in BNBC. But AC 705 for many editions, including '05 edition, has a very useful exemption from. Okay, let's read this. Vertical structural irregularities of types 1A, 1B, or 2. Soft story, extreme soft story, or the last one we looked at, the mass or weight irregularity. Okay, so soft story, extreme soft story, or mass irregularity do not apply. Okay, you don't have to worry about them. Where no story drift ratio under design lateral seismic force is greater than 130% of the soft story drift ratio of the next story above. I'm sorry, the word soft is not there. Let me read it again. So vertical structural irregularities 1A, 1B, and 2 do not apply where no story drift ratio under design lateral seismic force is greater than 130% of the story drift ratio of the next story above. Third type, no story drift ratio under design lateral seismic force is greater than 130% of the story drift ratio of the next story above. Torsional effects need not be considered in the calculation of story drifts. The story drift ratio relationship for the top two stories of the structure are not required to be evaluated. Okay, so I just want to tell you that this is another exemption which is much less important. So we once did that building. This is 16 feet ground story, 12 feet typical story. And that made it a soft story building going by AC 705 definition. The 70% differential. So story the story stiffness is less than 70% of the story stiffness above, or less than 80% of the average stiffness of the three stories above. By that definition, this was a building with a soft story. But when we calculated deflections, we were able to show that we fall under the exemption and that we do not have a soft story. So that one is very, very useful. Why BNBC has not adopted it, I do not know. And since BNBC has not adopted it, you probably cannot take advantage of it. But I kept it in so that you can take a look at how you can get around these irregularities. Okay, this is a FEMA slide that tells you the same story as our slides already. So this weight irregularity exists if the effective mass of any story is more than 150% of the effective mass of an adjacent story. Okay, Exception. Irregularity does not exist if no story drift ratio is greater than 1.3 times drift ratio of story above. This is a very, very powerful exception. The second exception I wouldn't emphasize. Exceptions apply to type 1A, 1B, as well as to type 2, the mass irregularity. Okay. The next vertical type 3, this is horizontal. This is, let me see if I can get rid of vertical irregularity type 3, vertical geometric irregularity. Okay, vertical geometric. Horizontal dimension of lateral force resisting system in story. Horizontal dimension of lateral force resisting system, which will be a frame or a shear wall in story, is larger than 130% of that in adjacent story. Okay, so that was our picture. This is the FEMA picture. Irregularity exists if the dimension of the lateral force resisting system at any story more than 130% of that. Okay, this is a definition that BNBC has altered. It has changed the definition. In BNBC 2020, the vertical type 3, the vertical geometric irregularity is defined as this irregularity exists for buildings with setbacks with dimensions given in the figure that you see in the picture. I'll let you study that, but I did want to point out that this is a change that BNBC has made to the AC 705 definition of this particular irregularity, vertical type 3. Okay, the vertical geometric irregularity. The next, okay, no, continue with vertical type 3. If you have that, the AC7 restriction is that you will have to do dynamic analysis. That's the only thing that gets invoked. And this is true of BNBC 2020 also. Vertical type 4, in plane discontinuity. This one is very important and quite common. There is an in plane offset of a vertical seismic force resisting element, resulting in overturning demands on a supporting beam, column, truss, or slab. That is ASC 705 definition. The definition in BNBC is different. It says an in-plane offset of the lateral force resisting element greater than the length of those elements. So an in-plane offset of the lateral force resisting elements greater than the length of those elements. Okay, so this shear wall is coming down if there is an in-plane offset of more than the dimension of the shear wall, then it is. So in BNBC, there is a pretty nice picture. So upper floor, this is the shear wall, lower floor, this is the shear wall, and the B dimension is greater than the A dimension. So the BNBC definition is different, it is clearer, and maybe you should stick with that definition would be my advice. This is the FEMA picture, obviously goes with the ASC 705 definition. Irregularity exists if there is an in-plane offset of a vertical seismic force resisting element resulting in overturning demand on a supporting beam, column, truss, or slab. So this shear wall is coming down, then takes an offset and then comes down here. There is an overturning demand on this beam. So that is the ASC 7 definition in BNBC. If this offset is larger than the shear wall dimension, then we have this particular type of irregularity, type 4 vertical. If you have type 4 vertical, the elements supporting the structural members supporting the discontinued stiff element have to be designed using load combinations with overstrength factor. Very, very important requirement. Once again, structural members supporting the discontinued shear wall or stiff element have to be designed using load combinations with overstrength factor. That's extremely important. Then 25% increase in seismic forces in connections in diaphragms and collectors. And then uh, equivalent lateral force procedure will be permitted by ASC 705, but BNBC will have you do dynamic analysis. Any vertical irregularity, BNBC will force you to do dynamic analysis. The final one, weak story irregularity. Weak story 5A is where weak story lateral strength is less than 80% of lateral strength of story above. Lateral strength is the total strength of seismic force resisting elements. If you have columns or shear walls, how much total shear is carried by the columns and the shear walls. Okay, that would be the story strength. So lateral strength is less than 80% of the lateral strength of the story above. That's 5A. 5A in AC 705 is prohibited in design categories E and F, which do not exist in Bangladesh. If you have 5A irregularity, AC 705 will force you to do dynamic analysis. I'm sorry, AC 705 will allow you to do equivalent lateral force procedure, but B and BC will force you to do dynamic analysis. 5B, extreme weak story. The weak story lateral strength is now less than 65% of the lateral strength of the story above. We have said this is the worst of worst irregularities, 5B, extreme weak story. A building like that could very well have a soft story as well as a weak story. Typically, it is both, and it may even be extreme soft story and or extreme weak story. You have to be very, very careful with this. 5B, extreme soft story, is prohibited even in design category D. This is big. Okay, it is prohibited in design category D. I haven't checked if that is true in 2020 B and BC. I do not believe the prohibition is there, but please do check for yourself. I did not do a thorough check. AC 705 would not allow that, period, in design category D. Okay. Structures with a vertical irregularity type 5B shall not be, so where they are allowed design categories B and C, they shall not be over 2 stories or 9.1 meter in structural height. Okay, so even in the lower seismic design categories C and B, they have to be short buildings, 9.1 meters at most. There is an exception to that height limit. The limit does not apply where the weak story is capable of resisting a total seismic force equal to omega sub 0 times the design force described in 12.8. So if you are willing to make the weak story that strong, omega sub 0 times the strength that would otherwise be needed, then the height limit of 9.1 meters does not exist. I said have not found a similar requirement in BNBC 2020. This is the FEMA picture of the 5B irregularity. Tells you the same story in a slightly different way, and I need not repeat. So this is now quarter after the hour. I mentioned that I did not anticipate having time to go through the non-structural component part. So I will take the remaining 15 minutes or so to answer a few questions if I can answer them. Let me see. By now there must be a pile of questions. So, Maria, if you can get me the questions here. I was told that someone came up with 20 or more questions even before the beginning of yesterday's seminar, and I do not know if these are those questions from the same individual. Anyway, I will. Oh, yeah, Maria is saying that is true. The first one is different. Anyway, I'll read them. There isn't a whole lot of time. I don't know how many I can cover, but let me try. So, first question, what does constant velocity, constant acceleration, and constant displacement mean? What is the use of these terms to a structural engineer while designing a building for seismic forces? That is a very good question, except I do not know that there is no way to give you a short answer. We have to, I do not know. I would love to give a lecture on how you do seismic design using dynamic analysis, particularly or specifically modal response spectrum analysis. And then I start with the concept of the response spectrum. From that, we go to design spectrum, and in the discussion of the response spectrum, this constant acceleration, constant velocity, and constant displacement will become very clear. The word spectral, very briefly, the spectral displacement is the same as maximum displacement of a structure of specifically actually a single degree of freedom system, which means only one component of motion of one mass is possible. You see, it gets intricate in a hurry. So spectral displacement is the same as maximum displacement. Spectral velocity is actually spectral pseudo velocity because it is not equal to maximum displacement of the system, but very close to it. And the spectral acceleration is actually spectral pseudo acceleration because it is not the maximum acceleration of the system, but something very close to it. Okay. In a certain period range, we have constant spectral acceleration. The structural response exhibits spectral acceleration that is constant. In a different period range, the spectral pseudo velocity is about constant. And in a third period range, the spectral displacement tends to be constant. Okay, I know that that is not a satisfactory answer, but that's the best I can do. You have to get into structural dynamics a little bit to understand those concepts. How does it affect you as you design your building? That is difficult to say. Most applications you probably need not be concerned, but then some of the time those things come into play. We have to be aware. Okay, second question. To compute deflection limit, except earthquake load, BNBC table 612 have different construction scenario, I think. Here, what is the difference between roof members and floor members? Here, deflection limit is different, so that my question arises. I don't understand that. Let me look up what table 612 is actually. Oh, table 612 deflection limits. Let me see. To compute deflection limit except earthquake load, BNBC 2020 table 612 have different construction scenario. I think here, what is the difference between roof members and floor members? Difference between roof members and floor members should be should be obvious. Roof member is part of the roof. A floor member is part of the floor, and we do have different, sometimes different limitations because the everything is different. You know, the roof has. Does not support as much load, but anyway, roof member and floor member, I think, are obviously different. What is different? Okay, here deflection limit is different, so my question arises. Yeah, deflection limit. So deflection limits for roof members say roof members supporting plaster ceiling, roof members supporting non-plaster ceiling, and roof members not supporting ceiling. Floor members, the one number that is given is the same as for roof members supporting plaster ceiling. Yeah. So it is. I do not know what needs to be explained. So if it is a roof member not supporting a plaster ceiling, then the we can tolerate more vertical deflection. That's all that the table is trying to tell you. So this gentleman had a lot of questions. To calculate story drift other than earthquake loads, there are criteria to less than or greater than zero point 0.7 time period. Here, yeah, I know what you are asking, but I did say that uh, the interstory drift limits under non-earthquake forces are something that to me do not make a lot of sense. Particularly the limits are in terms of building height rather than story height. So I find it difficult to take them seriously. The period of 7/10 of a second, they do not tell you how to calculate periods. So the only thing you can realistically do is to take the period out of the earthquake chapter. And so most people, I think, when they have to figure out the period, will take the approximate period out of the earthquake chapter of the code. If I were you, that's what I would do, because you have no other, nowhere else are you given a period calculation. Why you have different things for period less than 7/10 of a second, more than 7/10 of a second, less than 7/10 of a second will be a more rigid building, more than 7/10 of a second will be a more flexible building. That's all. But I have no taste for those uh, uh, interstory drift limits under non-earthquake forces. Okay, how it doesn't proceed somehow. Okay, let me go to someone else's question because it is not proper for someone to nominate. Okay. Uh, okay, the first question from someone else. AC 702 or O5 allows the use of steel ordinary moment frame with some height and dead load limitations for structures assigned to seismic design category D and E. That is true. Does BNBC 2020 allow the use of ordinary moment frame for seismic design category D with similar limitations? I have not checked into that, but Dr. Rakib will teach a course on the steel chapter of AC7. I don't steel chapter of BNBC. Whether it's one course or two, I don't remember now. So I'm sure that will be cleared up. It's chances are it is the same. That would be my guess. What you say about AC7 is very true. The BNBC steel chapter I have not checked, so I cannot directly answer your question. I would be surprised if it is not the same, but Dr. Rakib will go there. I don't remember the date. Another question from the same gentleman. Do we need to consider the 30% additional load in orthogonal direction described in BNBC for response spectrum combinations? What does that mean? So when you are doing modal response spectrum analysis, if it is 2D analysis, it is the same thing. You still have to do. So whether it is equivalent lateral force or modal response spectrum, the orthogonal direction, if you do 2D analysis, the orthogonal direction, let me think. Yeah, the orthogonal combination procedure will be the same. It seems to me. I am probably not doing my best thinking, but if I think otherwise, I'll let you know. My answer at this point will be the same.
I don't think you can do, if an orthogonal analysis is required, I don't think you are permitted to do a 2D analysis. You have to do a 3D analysis.
Yeah.
That's the same as this one.
Okay, so that gentleman also had a lot of questions. Let me go to another one. This is steel structure, which I would leave for Dr. Rakib. Let me see. All steel structure questions, which I have not really covered. I don't know. Let's see. Is it always adequate to take 30% earthquake load on orthogonal direction in horizontal earthquake load distribution? I'm not sure what the question is. If you are questioning whether 30% is adequate or we should go to something like 40%, 30 is what is required. If your judgment tells you you should take more, you are free to, but I have never seen anybody do that. Next question, how to calculate diaphragm flexibility of steel building for defining a building flexible or rigid? I have gone through SDI diaphragm design code, but it seems very hard to calculate for me. So today all steel questions for some reason. So SDI is Steel Deck Institute. Okay, now the diaphragm flexibility, or whether it is a stiff diaphragm or a flexible diaphragm, does not depend on whether it's a steel building or a concrete building. Diaphragm flexibility is defined very, very specifically in AC 705. I believe the section number is 12.3. I can check very quickly. I am pretty sure it's 12. Let me see. Yeah. So 12.3 is the section where you will find answers to flexible versus rigid diaphragm. There are diaphragms that are prescriptively flexible without having to do deflection calculation. And there are diaphragms that are prescriptively rigid without having to do deflection calculation. If your diaphragm is neither prescriptively flexible or prescriptively rigid, then you have to base your definition on calculated diaphragm deflection. And that's where I think your SDI document comes in. It will tell you how to calculate diaphragm deflection. But the definition is in section 12.3 of ASC 705, and that's where you need to look. I probably will take one more and then have to go because I have another meeting coming up. Okay, can you get me another question?
What about this? Oh, no, that's to you also.
Okay, I'm picking at random. This is a three-part question. Which load case and or combination shall be considered for checking drift? Which load combination will be considered for checking drift? The, the real answer is that unless you have a very unsymmetrical building, gravity loads do not cause lateral deflection, does not cause significant lateral deflection. So the drift that we are talking about is caused by the earthquake forces or wind forces. And wind and earthquake are never considered simultaneously. So you will calculate drift due to wind and try to keep, I shouldn't say drift, you will typically calculate deflection due to wind and keep it within the tolerable limit, which is height over 500. And you will calculate interstory drift due to the design earthquake forces and keep them within tolerable limits as given in SC7 or BNBC. Okay. In calculating the seismic deflections, remember interstory drift is deflection at level X minus deflection at level X minus 1. In calculating those, if you keep the gravity in place, that would be fine. The gravity that you should keep in place should be, I think BNBC tells you dead plus 1/2 of the live load. Anyway, what I'm trying to tell you, it should not make any difference unless you have a distinctly unsymmetrical building. Gravity loads are not going to contribute significantly to the lateral deflections. So what load combinations is not irrelevant, but it's kind of a non-issue. Which load case or combination shall be considered for checking torsional irregularity? Torsional irregularity does not have anything to do with load combination, is it? Torsional irregularity I gave you, when you calculate the deflections. Again, I see. Okay. My answer will be the same. We are talking about the lateral deflections. And when we are talking about torsional irregularity, we are really talking seismic. So it is the deflections under the strength level seismic forces that are important. And if you want to be, I would say keep the gravity in place. Dead plus live would be fine. Dead plus a little bit less than the full live load would be fine. But to look into load combinations is not something that is called for. In what condition would we consider a shear wall to be cracked? and when uncracked due to analysis. That is very easy to figure out. You run an analysis based on whatever assumption. If the bending moment that you calculate is more than the cracking moment, then the shear wall is cracked. If it is not greater than cracking moment, then it is uncracked. Okay. That is probably, yeah, it is approaching 1:45. Okay, I will quit here. Yeah, the question and answer part I know has not been very satisfactory. The time isn't there. The questions are not always well formulated. And I do not know what the solution is, except that once this rush to do the seminars is over, we'll try to see if there is a solution that can be found. Okay, thank you very much for your attention. Hopefully you have benefited from the 2 days of earthquake resistant design by BNBC 2020. And I believe next week, Professor Abedin and Professor Ansari will talk about the geotechnical aspects, and I am looking forward to both seminars. Thank you very much.